we were in the midst of discussing the singleton pattern as used in Java code. We realized that threading and synchronization forms a very important part of being able to create singletons correctly and ensuring that there is exactly one instance of a particular object. Let's look a little further at threading and especially synchronized methods. We just learned that associated with every object in Java is an intrinsic lock, and this lock can be applied by using the synchronized keyword. Now, when the synchronized keyword is applied to a method, it locks that method belonging to that particular object. Let's take a look at how this works here. Here is some code on screen which uses the synchronized keyword in methods. Here we have a synchronized counter. It has a private integer variable c, which is the actual counter. We have methods which can increment and decrement this counter, and one method which returns the value of the counter at any point in time. If you notice, all of these methods are synchronized. Increment, decrement, and value. All of these methods are synchronized. Any method in Java can be marked as synchronized in this fashion. Now, what does it mean for a method to be synchronized? It means that the lock that is associated with that particular object of synchronized counter applies to code within those methods. It means that only one thread can be executing this member function on this object at any point in time. It's worth pausing here and repeating this. On this particular instance of synchronized counter, one instance, only one thread can implement any of these methods. All of the synchronized keywords work on the same object lock, which is one instance of the synchronized counter. This means that if you have thread A, which is currently executing the increment method, you cannot have thread B execute decrement or value because they're all synchronized on the same lock, which is that instance of the synchronized counter. Take a while and absorb what I just said. The synchronized applies to the instance of synchronized counter, so no two threads can implement any of these methods at the same time. Now, if you're very careful about making a method synchronized, this can hugely help eliminate thread interference and memory consistency errors. These errors are generally caused when two threads try to access the same piece of memory at the same time. By having the synchronized lock around code which accesses that piece of memory, and in this example it's the counter, we can eliminate thread interference and memory consistency errors. Remember, it's important to know this, that only one thread at a time. This applies only to the method of the same object. Say you set up two counters, counter 1 and counter 2. The synchronized applies to counter 1. That means no two threads can access counter 1. The synchronized on counter 2 applies to counter 2. You're not synchronizing access across all instances of counter. The synchronization is on only one instance. Now, if you try to use this kind of synchronized to control access to a static class variable, not an object variable, it will not work and you will have errors as a result. This is because the synchronized locks on an instance. We saw what synchronized methods look like. Let's now look at synchronized blocks of code. These blocks of code need not be in the units of methods. They can be any lines of code within a method as well. Now, Since every object in Java has an intrinsic lock associated with it, it's possible to lock any section of code by marking it synchronized. So any number of lines of code, whether it's a whole method, half a method, 3 lines in a method, can be locked by using synchronized. And the way we do it is not by specifying the synchronized keyword on a method as we saw earlier, instead with code which looks like this. We can simply say synchronized and pass in this, and the lock is made on the this instance, that particular object to which that code belongs. In fact, marking a method as synchronized is just a shortcut. It's the shortcut to mark all the lines of code in that method to be under the synchronized block. So basically, marking synchronized on a method is the same as specifying synchronized and in brackets this for all the lines of code that exist within a method. There's an important point to note here. A thread can never block on itself. This means that if a thread holds a lock on an object, it can call all synchronized methods which are locked on the same object. If you go back and think about our synchronized counter example, if the thread is calling increment, that same thread, while holding the lock on that object, can call decrement and value as well. Because the lock is on the same object, once it has the lock, it has access to all sections of code that are behind the same lock. So a thread never gets blocked on itself. One synchronized method of an object can always call another synchronized method of the same object without blocking. Since every object has an intrinsic lock or a monitor, any object can be used as a lock using this synchronized statement. You can say synchronized and in brackets pass in the instance of an object which you have stored in a member variable. It need not always be this. The synchronized keyword helps with thread interference and memory consistency errors. Let's now look at thread contention. As synchronization and locks are very, very powerful, and just like any power, they can be misused and lead to other problems. These other problems are thread contention problems. Let's look at how synchronization and locks can cause thread contention, how this power can be misused. Deadlock, live lock, and starvation. These are 3 ways by which thread contentions can occur, and where use of the synchronized keywords exacerbate all 3 of these. So what is a deadlock? Deadlock occurs when 2 threads, each of which is blocked on a lock held by the other, which means both the threads are deadlocked. They can't make any progress at all. So if you imagine there is thread A and thread B, and there is lock 1 and lock 2, and both these threads need both these locks to continue. In such a situation, if thread A holds lock 1 and thread B holds lock 2, and neither of them have given it up and they are waiting for the other lock, the threads have stalled, they're not making any progress, they are in deadlock. A live lock means that the threads are not really stalled. However, 2 threads don't make progress. They keep blocking on locks held by the other. Neither move forward quickly. So they repeatedly contend for the same locks and they don't make much progress. This is not a deadlock where the 2 threads have stalled completely. Instead, these threads constantly interfere or contend with one another on the same set of locks. What is starvation? This is a very literal term and you'll soon see how that is so. Say you have 2 threads. Both of them require the same set of locks. Now, thread A is very greedy and keeps acquiring locks and refusing to release them. This will cause thread B and any other threads which need the same set of locks to be unable to get anything done. The remaining threads will simply starve for the lack of resources. In this case, the resources are locks which they are not able to acquire because thread A has accumulated and hoarded it for themselves. Code is truly like life. Maybe I should amend that. It's like corporate life. After this really long segue into threading and synchronization, both of which are core to the implementation of singletons, let's go back to a few last words about creating singleton objects. Make sure your singleton objects can't be cloned. Now, Java provides a way for every object in Java to be cloned. There is a .clone method which belongs to the object class, and all Java classes derive from the object class. Now, this .clone method should rightfully have belonged to the clonable interface. Instead, when the original Java specification was set up and the code was written, it was moved into the object class where it doesn't really belong. What's the implication of this? This means that all objects have a clone method and can potentially be cloned. But if you try to clone an object that does not implement the clonable interface, a not clonable exception is thrown. So to kind of work around the functionality that we don't really want all objects to be cloned, if your object does not implement the clonable interface, a not clonable exception is thrown when you try to call clone on that object. So you need to make sure that your singleton class does not implement clonable, because you want it to be a singleton. You don't want there to be other objects of the same type. For some strange reason, if your singleton class does implement clonable, override the clone method to throw an exception. You want to clearly indicate that cloning a singleton is just not allowed. Override the clone method to throw an exception. A few parting words. The singleton is a very powerful design pattern and widely used. However, instantiating just one object of a particular class is not as easy as it sounds. Exercise precaution. Make sure you use double-check locking. Make sure you lock correctly. And avoid making your singleton clonable.